Hello? Great. Hello, everyone. I think it's time to start. I'm happy that this microphone starts working. And, okay, so give me just a few seconds to set up the Zoom recording because our camera today got problematic. Seems that it won't work, but let's see. Our team will try to fix. And other than that, I think we're good. Other than that, I think we're. Does it work? Okay, great. It's time to start. So first of all, let me emphasize again. So our final exam will be online on Canvas, and it's right time as scheduled by our university is December 15th. It's Wednesday, from 8 a.m. to 10 a.m. So it's pretty early. Don't miss it, because the time window to take that exam is that window. We won't change. And I believe everyone knows how to get to the quiz, right? But later we'll say we'll send a reminder about time how to reach the exam. Is under the quiz section. You click it, you'll see that there's final exam. Just click into that and just do that. Just answer the questions, right? So most of the questions are just single selection or multiple selection. There might be a few questions asking you to write down your understanding of something or clarify something that's totally conceptual. There won't be any calculation like tell me how to compute the information gain or Gini index. We won't ask you to do that, but just all the basic concepts and verify you indeed understand the ideas and philosophies, all kinds of stuff we have discussed throughout this semester. So honestly, compared with the homework problems, it is a lot easier, but this is just a chance to let you go through the slides we haven't discussed so far. So we do recommend you to look at those slides we have discussed. And this exam is totally open book. So I mean, you don't need to memorize anything, but you are now allowed to text to each other and also post the questions to some online forum. That's not allowed. Okay, any question regarding the schedule of final exam? Great. So I will keep reminding you, right? So if you please bear with us, because we always worry about some students just miss those exams. That's not good, because it's pretty hard to reschedule another exam and to give you another set of problems. Okay. And another thing is that if you haven't started the final homework, the homework 5, please start right now. It will be due on this Friday. So please hurry up, because the final exam will be on next Wednesday. So you do need, I believe you do need some time to look into, to go through the slides to have some general view of the content. Okay? So please leverage the office hours and ask for help and to finish your homework 5 in time. Okay. So today we're going to talk about another commonly used Bayesian learning model. It's called naive Bayes classifier. So when we talk about a Bayesian learning, we actually introduce two notions, right? One notion is just to learn a probabilistic concept, meaning that we're trying to learn to predict a probability rather than the label, right? So we want to predict the chance or the probability that this instance has label 1, right? Rather than directly map this input to -1 or +1, right? So a typical example of such learning is called logistic regression, which we have discussed in the last lecture, right? So now we're going to talk about another very commonly used but fundamental Bayesian learning model. It's called naive Bayes classifier. Okay. So we'll first introduce the definition or the formulation of naive Bayes classifier and why it is called naive Bayes. We'll see later, right? Then we'll talk about how to learn that. So you see that the naive Bayes classifier is determined by many parameters. Actually, you see that you're essentially to learn a set of tables. Right? Each table actually records the probabilities of given some label, how likely it will generate each particular feature value. And but the learning through the maximum likelihood estimation principle, you see that it's really simple. The learning rule is just count and calculate the ratio. It's very intuitive, but it can be justified by this maximum likelihood estimation framework. Okay, so first, let us look at what is naive Bayes classifier. Right? So the key idea here is that we're going to use some probability distribution, a probabilistic model, to model both the label y and the input feature x. So this is different from logistic regression, right? So when we talk about logistic regression, we actually model the probability that given x, right, given the input vectors or feature vector, how likely the label is 1 or 0 or -1, right? But here for the naive Bayes model, our model components not only consider the generation of the label y, but also the generation of the feature values x. So that's why the naive Bayes model is also called a generative model, right? Because it considers how you generate the feature values. Right? So, but let us first use Bayes rule, right? Consider using Bayes rule to predict the label y given the input x. Right? So that is the conditional probability of big Y taking some label y, small y, given that your feature value takes some small x, right? And then we can apply the Bayes rule. So it is the joint probability of x and y, meaning that the prior probability that your label takes this small y, multiplying with the conditional probability or the likelihood that given your label is this small y, your feature value takes x. And then divided by the marginal probability that your feature value is x. Remember, this marginal probability has marginalized out all the choices of y, right? So it is constant to any y value, right? So we often view this as the posterior probability of the label being y for this input x, right? So now, suppose we have already had this formula, right? We know what is the probability for big Y. Label takes different values. What is the likelihood given small y? The x takes different values, right? And how do we make prediction? Right? Suppose we know how to compute this posterior probability, right? You have a set of choices for y for the labels y, right? And how do you pick up the y as your final prediction? What? Sigma y function? Yeah. Oh, well, let us suppose, okay, we know this label can be 1 or 0, and we know the posterior probability that label is 1 and label is 0, right? So now how do you decide which is your final label to predict. Yes, right? Because you know how to compute given this feature values, right? And the probability your y takes 1, takes 2, takes 3, takes 4, whatever, right? And now you need to determine which label is the best prediction, right? So we're gonna use the label who gives the maximum posterior probability, right? So this principle is called map prediction. Right? It's called map prediction. And we know that this maximum, right, is actually only determined by the numerator, right? The prior of the label takes small y, and the likelihood that given this label small y, and the feature value takes this this small x, right? And the denominator is actually constant. It's positive constant. So the maximum of this is actually the maximum of this numerator only, right? So actually only need to maximize the prior multiplying with the likelihood, right? So this is called a map prediction. Why it's called map prediction? Because we apply it in determining the final prediction, right? Still using the maximum A posterior principle. But it's not the map learning, right? So remember the map learning, we actually use this to determine which particular hypothesis in the hypothesis space should be the best model, right? But here we assume the model is here. This model is given. This H is specified, right? We know how to compute this joint prior probability, how to compute this likelihood. We know all the model parameters, right? But we still need to make a decision given this feature vector, what is the label should we predict, right? And how to do that, and we still maximize the posterior probability of the label, right? So this is a rule when we do the prediction. Any question? It's just like using map principle also in the prediction step. Right? And previously we talked about map principle or map framework training or learning procedure, right? But you can see that even the model is given because we model both the generation of x and y, right? So when we make a prediction, we're going to still use the map principle to find the label who has the largest posterior probability given you have observed this feature vector. Any question? This is a rule. I mean, this is a general principle when we apply the naive Bayes models to make prediction. Meaning that after we have learned that, we know how to specify the model, right? But when we make a decision, we still need to consider both the prior probabilities and the likelihood probabilities. So to emphasize, right? So we know that when we make a prediction, we need to consider the prior probability of the label being y, and also the likelihood of observing this input x when the label is y, right? This is a prediction rule. But from this prediction rule, we have already known that we need to know the set probabilities here in the prior and the set probabilities in the likelihood, right? So that means in our learning, we need to learn what is the set probabilities. What are the two sets of probabilities? What are the prior probabilities that the label y takes different values? And what is the likelihood probabilities that conditional on different label, the feature x takes different values. So you can see there are two sets of probabilities that need to be learned from data. Okay, so maybe that still sounds a little bit abstractive. Now we're gonna use this example again, right? Tennis example, when we use that to showcase how we run the decision tree learning algorithm, how we construct decision tree. We're gonna use this example again, right? So once we have identified the naive Bayes model, that actually means that we know two sets of probabilities. One set of probability is the prior probabilities, which is this top table. It tells us that without any other information, right, what is the prior probability that I should play tennis today? Right? So you can see that this is 0.3, yes, and 0.7, no. So basically from the data, from the learning procedure, it tells us that my prior preference is to be staying at home, right? I do not play outside very much. And then the likelihood probabilities actually consists of two tables. Right? One is conditional tennis is yes, meaning that conditional my decision is yes. What is the probability that the temperature takes some value and the wind takes some value, right? So in the temperature and wind are just weather conditions, right? We have several different values that can be taken. Like temperature can be hot, cold, and mild. Wind can take like strong, weak, right? So actually, we have learned from data that given I play tennis today, and the temperature and the wind takes different values, what is their chance? Like for example, given tennis is yes, then the probability that today is hot and has strong wind is 0.15, and today is hot but wind is weak is 0.4. Right? And today is cold and wind is strong is 0.1. It's right. It's much less likely, right? And also, we also learned that given that I do not play tennis, what is the probability that temperature and wind take different values? Like given that I do not play tennis, I stay at home, the chance, the probability that today is hot and strong is 0.4, right? And today is hot and wind is weak is 0.1, and so on. So these two tables tells us on days that I do play tennis or I don't play tennis, what is the probability that the temperature is some specific T value and wind is specific W value. So those are all the model parameters. Okay. So once we have learned those parameters or probabilities from data, we're now ready to make prediction. Right? For any weather conditions, I'm gonna play tennis outside or just stay at home, right? So now let us use an example, right? Suppose I have observed that today is hot, right? And but the wind is weak, right? I'm gonna use this set of parameters, right? This actually specify a model to make prediction, should I play tennis or not? Right. According to our prediction rule, we should compute the maximum, the label who gives the maximum posterior probability. That is the label given that temperature is hot, wind is weak, who is maximum, right? So, which is essentially to maximize the product of the prior probability, whether play or not, multiplying, given my decision, the likelihood of hot temperature and weak wind, right? So now let us try to calculate, right? So we have two labels, right? Yes or no, right? So when play is yes, and the prior probability of yes is 0.7, right? You just read out table 0.7, and then given yes, temperature is hot and the wind is weak, is what? here, right? Just look at the entry in table 0.4, you multiply them together, you got 0.12, right? Now, we need to consider the case for another label where play is null, right? So the posterior probability that play is null given H and W is proportional to the prior probability null and the conditional probability or the likelihood given null, temperature is hot when it's weak, right? So the prior probability of null is 0.7, right? And given null, what is the probability H and W? We just look at the entry in this table, right? So it's 0.4, no, it's hot, and weak is here, 0.1, right? So now you just multiply them together, you got 0.007. So now, which label should we predict? Yes, right? Because our rule tells us we should predict the label who gives the maximum posterior probability, right? Which is proportional to the prior multiplying with the likelihood, right? So by looking at these two label choices, we found that yes has the maximum posterior probability. So we're gonna predict my decision as yes, right? Any questions so far? Number of features or what? Yes. Yeah, of course. Actually, you might have a lot of features. Here, just give two features for an example, right? Maybe in practice, you have 100 features. So we'll talk about if you directly learn the all combination of this, it will be extremely expensive and very large the model. So that's why we're gonna introduce the naive Bayes assumption. But the whole model framework is like this. We're gonna model the prior probability of you take each particular label, right? And then given each particular label, what's the chance those features take the values, right? Once we know all those parameters, we can make prediction with this MAP principle again, right? So any question regarding the model framework? Is everyone comfortable? Sounds great. So now, let us talk about the learning problem, right? So now we're going to look at a more comprehensive data set, right? It is the 14 examples we used for our decision tree learning, right? So actually you have 4 features, right? Not only the temperature and the wind, right? It also includes the overcast. The humidity and the outlook, right? And the different features can take different values, right? Outlook may take sunny, overcast, and rainy. Temperature might be hot, medium, cool. Humidity can be high, normal, low. The wind can be strong, weak, right? So once we know the feature set and the values that each feature can take to learn a model based on this problem, right? We need to learn, again, we need to learn 2 sets of probabilities, right? So first, what is the prior probability without seeing any data, right? Or is there prior preference you play yes or no? And second, what is the likelihood probabilities? Namely, given some specific decision, yes or no here, what's the chance your 4 features takes different value combinations, right? That's conceptually how should we estimate our naive Bayes model, right? So now let us look at these 2 sets of probabilities one by one, right, and say What's the problem here? So first, to determine the prior probabilities, right? How many parameters do we need? Just one, right? Because although, I mean, we have two labels actually, we have yes or no, right? But we know there are prior probabilities should sum up to be one, right? So actually, you don't need you only need one number, right? And the prior probability for another label is just one subtract that number, right? Subtract one by that number, right? So so a single number is enough to determine the prior probability. That sounds comfortable, right? And now let us look at the likelihood probabilities. So as we mentioned, right, we got four features. And we need to know conditional on each value of the label, either yes or no, right? We need to value for each possible assignment of these four features. So now let us try to calculate how many numbers do we need to determine these likelihood probabilities. Right? So for x1, meaning the outlook feature, we got three values. For x2, which is the temperature, we got three values. For the humidity feature, we got three values, and for wind feature, we got two values, right? So now I want to ask to determine this likelihood probabilities given a specific choice of play or yes, a play, right? So how many numbers do we need? Any thought? Can you tell me how to calculate? We're not good at like just giving a number. Any thought? Why? Yes, perfect. Yeah, very good, right? So remember, given yes, right? You can imagine the probability of all the combinations of this x1 to x4, their summation must be one, right? So that means the number of the probabilities you need to know is actually corresponds to the number of combinations of those values. So, but of course, because their summation is one, right? You actually only need the total number of combinations minus one parameters. Okay? So now let us look at how many combinations do we have in total, right? X1 takes 3, X2 takes 3, X3 takes 3, and X4 takes 2 distinct values, right? So the number of combinations is just 3 multiplying 3 multiplying 3 multiplying by 2, and subtract with 1, because the probabilities of all the combinations should be should add up to 1, right? So only need this number subtracted by 1 parameters. But this is just for one assignment, right? Because this is just the tells you, okay, given play is yes, what is the likelihood of x1 to x4 takes different values. You have to also estimate when play is no, right? Is negative. What is the likelihood of x1 to x4 take different values? So what's the problem here? It take a long time. Well, I actually we need a little bit more accurate. Actually, it's not saying taking a long time. It's actually take too many parameters, right? Like you have only 14 examples, but how many model parameters do we have? Like 3 multiplying 3 multiplying by 2, like this is 54. right? -1, 53 times 2, like 1/6, right? Plus these two parameters, right? You can see that model parameters even much larger than number of examples. That can make your model overly complex, right? So let us consider a more general case, right, to say why like straightforward modeling is so ponderous. So suppose our label y in general has k labels, right, to determine the prior probabilities that we need k-1 parameters, right? Because their summation must be 1, right? So you just need k-1 parameters. The left parameter is just subtract 1 by the summation of the remaining, right? So there's nothing to worry about here, right? But the problem is the likelihood. To make things easier, is simpler, right? Let us just assume we have D features, but each feature just take 2 values possible. So it's the balloon features. So for each particular choice is Y, we need to know the likelihood parameters to determine this conditional probability, right? And how many numbers do we need? Consider for that, I mean, explain to me why we need this number of parameters. Yes, exactly, right? So given some particular label y, say y is 1, right? So determine this, we need to consider all the combinations of x1 to xd values, right? So each feature has 2 possible values. So you have 2 to the power of d possible combinations. And the probabilities for those combinations, their sum must be 1. So of course, to determine those probabilities, you only need 2 to the power of d minus 1 parameters, right? But this just determines for a particular choice of label. But you have k choices label. So you got multiply k outside. So you can see that overall, for the likelihood parameter, you need k multiplying 2 to the power of d minus 1 parameters. That will be a giant table. And the problem is that you can see the number of parameters grows exponentially with number of features. That's a major challenge. That means we need a lot of data to estimate so many parameters. Any questions so far? So just the naive or the straightforward formulation, right? But we can see the bottleneck here. The number of parameters grows exponentially to the number of features, right? Even you only have a balloon features for, you have balloon values for those features. So the consequence is that because you have to estimate so many model parameters, actually gives a high model complexity, right? And you don't expect that your number of training examples can grow also exponentially, right? It's very hard because the collection of training examples is costly, right? Then if your number of training examples is far less than number of model parameters, it can easily overfit, right? And how can we deal with this problem? If we don't make any extra assumption, right, we actually choose a very big hypothesis space, right? Because there are so many model parameters, right? Each set of model parameters determine one space model, right? You have a lot of models. That means hypothesis space is too large, too complicated. So now we want to simplify the model, right? That means we want to reduce the hypothesis space to make it simpler so that we can avoid overfitting issue or leave it overfitting issue. And the key idea for naive Bayes is to make the so-called actual independence assumption. Right? That's the key. So we call this independence as a conditional independence. So what is conditional independence? Right? Suppose x, y, and z are random variables. We said x is conditionally independent of y given z if the probability of x is independent of y when z is observed. Right? I think it's more succinctly represented by this formula. So basically it says condition on z, the joint probability of x, y is the product of conditional probability of x given z and product of y given z. That's it. It's very similar to the definition of independence, except that we need to add some conditional part. It can also equivalently written as given z, the conditional probability of x given y is just the probability of x given z. It's the same thing. Any questions so far? Okay, so now let us look at how we inject this conditional independence into our naive Bayes model. Okay? So if we do not make any assumption or any structure within this likelihood, P of x1 to xd given y, right? It will require like k times 2 to the power of d minus 1 parameters, right? The k comes from enumerating the possible values that y can take, right? And 2 to the power of d minus 1 comes from enumerating all possible configurations of x1 to xd values, right? So now, to simplify this, right? We assume all the features were conditionally independent given the label y. This is called the naive Bayes assumption. So now we can simplify the conditional probability of x1, x2 to xd given y as the product of conditional probability of each individual feature given y. This is our assumption. So now I want to ask, given this assumption, how many parameters do we need to determine this conditional probability? Can I explain a little bit? Mm-hmm. Mm-hmm. It's not two, actually. So basically, give any specific choices y, right? I mean, you hit the point, but let me make it more complete, right? So given each specific choice one, right? Due to this factorization or conditional independent assumption, right? Each term is only determined by one parameter, right? Because x1 is either 1 or 0. We only need one parameter to determine. And the probability of x1 takes another label is just 1 minus that parameter, right? So similar observation applies to P of x2 given y, right? So basically, given any specific value of y, right, you only need one parameter to determine each term in the product. So you only need d parameters because you have d features. But that's only for one specific value of y, right? You have k possible values of y. So we got kd parameters overall. Compared with this, the k times 2 to the power of d minus 1 parameters. So now you can see the number of parameters is linear with the number of labels and number of features right now. Right? So it's not bad. It's much more simplified. Right? So that's why we take this naive Bayes assumption. We make this a strong assumption to reduce the hypothesis space to make our model much simpler so that we can avoid overfitting. Does it make sense? Okay, so now let us look at naive-Bayes classifier, right? So the key assumption here is the features are conditional independent given the label y. So then our learning will still require two sets of probabilities, but much smaller, right? So first, we're gonna still need the prior probabilities. And second, we only need for each particular feature j, right? J's feature xj, what is the likelihood of pxj given y, right? We don't need to consider their combinations. We only need to look at the conditional probability of each particular feature given the label. And once we have estimated those probabilities during the prediction procedure, we just apply this decision rule, which is MAP principle, right? We maximize the joint probability, that is the prior multiplying with the likelihood. Then, because the likelihood is further decomposed as a product of the probability of each feature j given y, right? You just multiply them together and you maximize this product and find which label gives the maximum, right? Which is our prediction. Any question? Mm-hmm. Because it reduces number of parameters. When it's reduced number of parameters, you can imagine your hypothesis space is largely reduced, right? So you can imagine, like, if I do not make such assumption, right? I just assume this. Actually, you have a giant hypothesis space. And the hypothesis space with this factorization assumption is actually a subspace. Must be a subspace of this giant space, right? You're actually reducing the hypothesis space. That's why you make your model much simpler, and you avoid overfitting. Right? We avoid overfitting just by making the model simpler. But someone may criticize, okay, your conditional independence assumption is too strong, right? But that's another story. And you can always choose some kind of trade-off. You allow groups of features that are conditionally independent. That's a kind of like trade-off. Any other question? Okay. So now we have finished introduction of the naive-Bayes classifier definition, right? So the remaining thing, the next thing is about how to learn naive-Bayes classifier, right? So, so here we're gonna use the maximum likelihood estimation. So suppose we have a data set D of m pairs of the input feature xi and yi, right? And want to learn a naive-Bayes classifier, which is determined by two sets of probabilities, right? So that means each specific hypothesis, H, is defined by the prior probability, P of y, and the likelihood probability given y, the feature j takes different values, right? So these two sets of probabilities determine one specific H. Of course, if you vary them, it corresponds to different hypotheses. Okay. So, and here for notation convenience, right? So we're gonna use the subscript I to denote I's example. So this bolded xi just means the ith input feature vector or ith feature vector, or ith the training example, right? And then when we talk about the j's feature in the ith example, we're gonna add one more subscript j. So here this xij, this unbolded small x, it just means the feature value. It just means the scalar. Xij means, okay, this is a j's feature in ith example. Okay. So once we have collected these m training examples, right, and want to learn this classifier in a probabilistic way, right? So then we need to choose a probabilistic criterion to select hypothesis. We're gonna use the maximum likelihood principle. This is just for convenience. Actually, we can also do the maximum A posterior estimation to learn naive Bayes classifier. But for just for simplicity, we're gonna ignore it. We're gonna ignore a component because adding that component is relatively easy. Right? So let us just assume that we don't make any preferences over the hypothesis, right? Or we assume the hypotheses are equally likely to be the truth. Right? So we only maximize the likelihood of observed data given this hypothesis to determine which hypothesis gives us the best fit to the training data. Right? This is a MLE, right? Maximum likelihood estimation. And we further assume, okay, each example in this data set is IID, right? Identically, independent, identically distributed. That means the likelihood, the likelihood of whole data can be further written as the product of the likelihood of each training example xi, yi, right? Given this hypothesis H, right? And this actually asks what the probability would this particular H assign to the pair xi, yi, right? And this is actually can be further decomposed as, the prior probability yi given this model. And given the yi takes this particular value, what's the likelihood your i's input example takes those feature values? Okay. So according to the naive Bayes assumption, this xi, remember, is a vector, right? It contains like, for example, a set of features, right? We further assume this conditional probability can be decomposed as the individual conditional probability of yi given each feature takes its particular value, right? So xij is the j's feature of i's example. Right? This is actually the naive Bayes assumption. Any questions so far? We just write down the likelihood, right? According to the RID assumption of the training examples, the whole data likelihood can be written as product of individual likelihood of each example, right? And the individual likelihood is further the prior probability of the label multiplying, given the label, the probability of the feature vector, right? And according to our naive Bayes assumption, we know that the joint feature values, for example, I, given the label yi, is decomposed as the individual conditional probability of each feature given yi. Right? So we end up with a bunch of terms in the product, right? So now, how do we proceed? Any thought? Yes, take logarithm, right? Remember, those are all like small numbers between 0 and 1, right? If you multiply a large number of values between 0 and 1 together, it's very easy to be truncated to 0, right? It's very easy to underflow. To avoid that, to be more robust, we always take logarithm outside of this product, right? Because it doesn't change the maximum, right? We just take logarithm, and then all the product operations becomes a summation, right? So it is equivalent to maximizing the summation over every training example, where in each segment, it is a log prior plus this is also over each training example. And over each training example and over each feature in each training example, log probability of each feature j in example I given the label yi under the current model, right? So now we have simplified our objective function or maximum likelihood function to this step. Right? What's the next step? So by the way, any questions so far about this derivation? I think it's pretty straightforward. Anyone, if you haven't taken any statistical class before, I bet you have seen this before, right? No question? Great. So now I want to ask, what's the next step? Right? We have known by taking the logarithm over the likelihood probability, we got a bunch of summation, right? We got summation over all the training examples, and summation over all the training examples, summation over every feature value in each training example, right? So what's the next step? Yeah, you need to consider how to represent this, right? How to represent this each probability, right? Otherwise, if you don't know the form of P of y given h, P of xi, j given y and h, how do you maximize the log probabilities, right? So now let us use some very convenient representation of these probabilities in terms of those model parameters. Right? So we need to make a model assumption about the functional form of these probability distributions, right? And for prior, we know that the label 1, we assume the probability y is 1 is p, so that the probability y is 0 is 1 minus p, right? So, and for the likelihood, for each feature given a label, right? Suppose we're still dealing with binary feature, right? So we can denote the probability y is, given y is 1, the feature j takes 1 by aj. And the probability, and so that the probability of xj taken 0 given y is 1 will be 1 minus aj. Right? And similarly, we can denote the probability given y is 0, xj is 1 is by bj. So given y is 0, xj is 0, now becomes 1 minus bj. Right? So now we have our set of parameters p and aj and bj, right? Those are all our model parameters. In other words, our hypothesis h consists of all those parameters like p and aj, bj's. So next, we're going to need to represent those probabilities in terms of p and aj's and bj's. That's our next step. And once we have identified this form, we can, take the derivative and set derivative 0 and find the optimal parameters like optimal p and optimal aj and bj and so on. Right? So first, from the prior definition, right? We know that when this yi is 1, so this should be p, right? When this yi is 0, this should be 1 minus p. So of course, we don't want to write down if else, right? We don't want to give two branches. We want to integrate them into one form. How can we do that? We don't want to explicitly consider two cases like when y is 1, you got this log p, right? And when y is 0, you got 1 minus p, right? This is really tedious, right? We just want to unify the form of p y given h by one formula. How can we do that? Any thought? We just use some product of the power, right? So we can write down this probability pyi given h as p to the power of this indicator. Y is 1, and 1 minus p power is indicator yi is 0. So this square bracket just is an indicator function. So it means that if yi is 1 is true, then this this bracket gives the value 1. Otherwise, gives value 0, right? And similarly, when y is 0, then this bracket function will give 1. Otherwise, it will be 0. So now you can see that. So this bracket z is called the indicator function, right? And its value is 1 if the argument z is true and 0 otherwise. Right? So now you can see that by using this one formula, right, we cover 2 cases, right? So you can say that if yi is 1, then this is indeed p, right? Because this power is 0. If yi is 0, then this power is 1, so you got 1 minus p, and this power is 0, so overall you got 1 minus p, right? This is a very commonly used trick in the in statistics. You represent the probability in one formula, no matter how your value of the label take. Okay. Any question? Okay. And for likelihood terms, we're going to use exactly the same trick. Okay. So for likelihood case, we know that, okay, given y equals to 1, xj is 1, we denote the parameters by aj, right? And correspondingly, 1 minus aj. And given y is 0, xj is 1, it's bj. And correspondingly, given y is 0, xj is 0, 1 minus bj, right? So now we can represent this conditional probability just by a product of 4 terms, right? So it actually represents the 4 cases of the combination of xj and y values. So when yi is 1 and xij is 1, we know this probability is just aj, right? It's here. So just put aj and you have this indicator here, right? Then multiplying with the second case where yi is 1, xij is 0, so you got 1 minus aj, and put the indicator function here. Right? And similarly, and yi is 0 and xij is 1, it corresponds to bj, you got your corresponding indicator here, right? And finally, yi is 0 and xij is 0, you got the indicator function here, and the value 1 minus bj. Right? So you can see that we use this product of 4 terms, summarize all 4 cases, all 4 combinations of xij and yi, right? Their corresponding probability. Mm-hmm. Yes, this is the definition of indicator function. This is just the indicator. It means that if yi is 1, xij is 1, right? So this statement is true inside this bracket is true, right? But all the other statements are false, right? So the indicator is just 0. So that means anything you take power of 0 is just 1. That's the trick. So actually, any indicator is 1 implies that the remaining indicators are 0. What? Yeah, in some sense, yes. But it's just the way like you integrate all possible cases together, right? You got one case, that means you got one case to be true, that means all the other cases are excluded, and meaning that their power is simply 0. So their terms are just 1. Okay. This is a very common used trick. Okay. Any other question regarding that? If you feel uncomfortable, just take a look at it for 30 more seconds. You get used to that. So the benefit is that once you just substitute those product of power terms for those probabilities, and you know, because they have some power, you take a logarithm, you can move the indicator in front of it, and then you can take the gradient and set gradient to be 0, and it's pretty straightforward. When you solve the gradient to be 0, the result is just the ratio. So, for example, the optimal prior probability that your y is 1 in P is just you count total number of examples whose label yi is 1. plus total number of examples. So just from like all 14 examples, just look at, for example, 5 examples are positive, and then your maximum likelihood estimation of P is just 5 over 14. That's it. And similarly, those AJ are just, which is the conditional probability given Y is 1, actually takes value 1. The optimal value of AJ is just to count the cases where your Y, the number of examples where your YI is 1 and Xij is 1, divided by the total number of examples whose YI is 1. It's very intuitive, right? But now we can justify it with maximum likelihood estimation. And similarly, BJ indicates the conditional probability given Y is 0, Xj is 1. So the MLE estimate is just the number of examples whose YI is 0, Xij is 1, divided by the number of examples whose YI is 0. I'm not going to derive this. I will leave it as an exercise for you guys. It's not hard at all. But I just want to point out, throughout this derivation, you see that the learning rule here are really, really intuitive. So I want to use this example to show how we learn those model parameters, namely those probabilities. So, and for naive-Bayes classifier to learn the tennis playing game, right? So first we need to determine the probability, the prior probability you play is yes or no, right? So according to our conclusion of MLE estimation, we know the optimal estimator of this P, right? Which is actually the total number of positive examples over the total number of examples, right? So we got 9 positive examples in total. There are 14 examples in total, so I have 9 over 14. So correspondingly, the prior probability the play is no is 5 over 14, just 1 subtracted by 9 over 14. And then let us look at the conditional probabilities or the likelihood probabilities. Given your play is yes, meaning that you're going to play outside today, right? What is the likelihood your overcast is sunny? Right? Again, just to look at the ratio, right? So first, we're going to look at how many examples whose overcast is S and play is yes. So got 2 examples. Here, the 9th example, and the 11th example. Okay. And then we're going to divide it by the number of examples where play is yes. So we have 9 examples where the play is yes. So just 2 over 9. Okay. And then similarly, if you want to determine what is the MLE estimation of the probability given play is yes and overcast is raining, right? We just look at how many examples where overcast is raining and play is yes, which turns out to be 3, right? So it divides by 3. We divide 3 by the number of positive examples, 9, which you got your MLE for this probability. And similarly, you can get your MLE for the third probability, like P overcast equals to this outlook. Sorry, it's called outlook. Outlook is overcast given play is yes, right? So gonna which is 4 over 9, right? Because you only have 3 values of the outlook, right? So you got 2 over 9, 3 over 9. So the remaining conditional probability will be just subtract 1 by 2 over 9 and 3 over 9, which is 4 over 9. Okay. And you can continue on this to get the conditional probabilities given play is no and how the features takes different values. Any questions so far? Everyone is comfortable? Okay, there's a, so here we just introduce a very straightforward idea to train the naive-Bayes classifier. But there is some issue here. I want to give you just give you an idea. So what if I cannot observe some value appear? Like for example, if I don't have the feature outlook takes overcast in our example, how should I estimate this probability? It's simply zero. Yeah, I saw someone said, why not put it zero? Well, zero is not bad, but it's not good, right? Because we need to cover all possible cases, right? So this is actually the issue of maximum likelihood estimation. So if your data is not dense or comprehensive enough to cover all possible cases, right? You need to ensure that every feature value must at least appear once in your data set, right? If it doesn't appear, well, you got zero probability. And if it happens that, okay, you're given a new test example where some particular feature takes that value absent in the training set, then your drawn probability is what? It's simply zero, right? We'll calculate your drawn probability. It's simply zero. If you take log, it's minus infinity, right? That will make your naive-Bayes classifier crash. How can I address this problem? Any thought? Add what? Add one feature value. How do you add one to each value? Yeah, yeah, that's a good idea, right? But actually, I want to speak of it in a more formal way. We're gonna assume that if even it's a feature value overcast never appears, it still has some chance, right? Might be very small, but we cannot make it be zero, right? How can we do that? Mm-hmm. Well, this sounds great, but this is not like missing feature. Suppose we have observed all those examples, but all examples do not have this O value in this overcast column. That's not like you have some example, but you have you don't you never say. That's not like something like that, right? You have observed examples, but you don't know the actual value here. But just assume, okay, suppose we only observe, we never observed those examples. Suppose we never observed those examples. We only observed 1, 2, 4, 5, 6, 8 to 10, 11, and 14, right? That means in all your examples, your overcast feature never appears. Then this probability will simply be zero. Of course, this is not what we want, right? And suppose next example, suppose this third example is your test example, then your probability will be simply zero. Okay? So that's why in practice, when we implement naive-Bayes classifier, we'll never directly use MLE because of this corner case, right? You need to ensure your data is complete enough, is dense enough to cover all possible features. And a more commonly method is using MAP actually. So right now we're assuming we're using MLE, right? We only care the data fitting, right? But don't care the prior. That means if your data is not complete enough, you're gonna have some trouble. Right? But right now, if we add some prior over each probability, like I can assume given play is yes, the outlook feature takes each of these three values is 1/3, right? And then when I combine with the likelihood, of course, this probability and this probability will get updated, right? And but for this probability, even I have never observed that, I can still maintain some kind of probability. Then during the test, I won't worry that my probability of the test examples will drop to 0. Does it make sense? Mm-hmm. Yeah, this performs better. And it's called smoothing. Is what he said. It's called smoothing. It's very often used in natural language processing because naive classifier is pretty popular in many text mining applications. So you always need, because the text corpus, the documentations cannot guarantee to cover all possible cases, right? You always have some absent. Right? If you just drop them to 0, you got some like a weird situation. And sometimes even your data observation is kind of sparse. You can imagine, suppose you only have 5 examples, right? And you got 1/5, 2/5. This is kind of like a too rough estimate because total number of counts is small. So when you add in some prior into that, you can smooth those uneven number of the counts. And overall, it will make your whole prediction much more robust. Any question regarding the idea? Yeah, this is just to give you an idea. I mean, how naive Bayes is practically implemented, but we don't require you to implement this. We just give you an idea. Okay, so we have a finished introduction of naive Bayes. So in the learning procedure, right, we count according to MLE principle, right? We simply count how often features occur with each label and normalize it to get a likelihood. That's it. And the priors are just the fractional examples with each label. And this can directly generalize to multiple classes. So don't worry about you're dealing with binary features or 3 features and 4 features and 10. I mean, 2 possible values for features, 3 possible value of features, or 10 possible value of features. Their MLE estimation is the same. Right? And the prediction is that we're going to use the learned probabilities to find the highest posterior probability. That is called map probability. We maximize the prior multiplying with the likelihood. Okay. To summarize, the K assumption in this naive Bayes model is the independence assumption. Namely, given the label, we assume all the features are independent to each other. In this way, we can largely reduce the number of model parameters. We make the model much simpler. We largely reduced hypothesis space. Right? And we use maximum likelihood estimation to learn. So learning pretty simple. It's just calculate the count and normalize it. Okay? And the prediction, we use the maximum A posterior principle, okay? As we just discussed. Okay? And this can further generalize to real value features, although we just discussed about the categorical features or binary features. And of course, maximum estimation learning has some problem from data when the data is incomplete or not complete enough. It might bring some problem. A common fix will be add some prior so that you can conduct the maximum a posterior learning as well. Any question? Great, thanks. Let's stop here.